The title of this week's lab is the electrical conductivity of aqueous solutions. We're going to begin our discussion of what properties of a substance allows it to conduct electricity. In order for a substance to conduct electricity, two different conditions must be satisfied. First, there must be charged particles present in the substance, meaning there has to be either free electrons, a cation, or anions. And beyond just having charged particles, these particles must be free to move. They must be mobile in the substance to allow for the circuit to be completed. So let's start thinking about this in terms of a substance we're all familiar with, water. Does pure water conduct electricity? Meaning, do the two conditions above, are they satisfied for pure water? To determine whether or not water conducts electricity, we need to understand its structure. Water, or H2O, consists of one oxygen atom and two hydrogen atoms covalently bound to one another. A covalent bond means that a shared pair of electrons is what is connecting the two atoms together. Overall, water is a neutral molecule, meaning there isn't an overall charge on the water molecule. On the right-hand side here, you see a picture of liquid water molecules. Liquid water is free to move about, and so we would consider these molecules mobile in the liquid state. So given our definition of what conditions must be satisfied for something to conduct electricity, water molecules are able to move freely, so they're mobile, but they're not charged. So in fact, pure water does not conduct electricity. Let's now consider another really common substance, table salt, or sodium chloride. Does it, in its solid form, conduct electricity? Well, if you think about sodium chloride, you probably know that it's a white solid. It's a rigid crystalline structure. And if we look at how the sodium and chloride are connected to one another, we see that they're in this very orderly pattern of a sodium cation next door to a chloride anion. It's ionic bonds that are connecting these atoms together. And in fact, electrons are donated by the sodium and accepted by the chlorine. So the sodium and the chlorine are both in an ion form. They're both charged. However, in this particular form, there is little to no mobility of the ions. So in this case, the atoms, or in this case, the ions are charged, but they're not able to move freely about the substance. Therefore, solid sodium chloride does not conduct electricity either. This then brings us to the question of why you shouldn't take a bath with your hair dryer. In order to understand why something like bath water does in fact conduct electricity, we need to look more closely at the structure of water. I mentioned previously that the oxygen and hydrogen atoms in the water molecule are covalently bound by a shared pair of electrons, and that overall this molecule is neutral. What I didn't mention is that the electrons are not shared equally between the hydrogen and the oxygen. In fact, the electrons spend more of their time near the oxygen, giving the oxygen end of the molecule a partially negative charge. This then means that the hydrogen end of the water molecule has a slightly positive charge. This separation of charges across the molecule is not the same as being an ion, but this is called a dipole moment. And you can look at the image on the right side of the screen. It shows a pictorial representation of this dipole moment, with the hydrogen end of the molecule being green, representing slightly positive, and the oxygen end of the molecule being blue, representing it being slightly negative. So now that you understand that the sodium and chloride ions are being dissociated from one another into the aqueous solution, we can represent this in the form of a chemical equation. I've shown it two different ways here. First, we're saying solid sodium chloride when placed in water, and I'm showing it breaks apart into a sodium ion and a chloride ion. And by this representation, we would understand that those ions are no longer bound to one another, but are free to move through aqueous solution. The bottom representation is saying the same exact thing, but now we use that subscript aqueous, or AQ, to understand that in fact the sodium and the chloride are not bound to each other but are dissolved or dissociated in water. In both of these forms, we are representing that the sodium chloride has dissociated completely, And so we represent this dissociation process, or the separation of the cation from the anion, by using a single arrow, because the process goes to completion. As I mentioned before, there are now charged particles that are mobile in solution. So sodium chloride solution, in fact, conducts electricity. So something like your bath water is full of ions that are coming off of your skin, that are found in the tap water to begin with. So tap water is not pure H2O. There are ions dissolved in solution, and that is why you should not take a bath with your hairdryer. We can further classify this type of compound that dissociates completely into its ions. So ionic compounds, so a cation and an anion, or a metal and a nonmetal, that dissociate completely into their respective ions in solution, conduct electricity well when dissolved in water, and are called strong electrolytes. That word strong electrolytes simply means that it conducts electricity well. So how do you figure out whether a substance is in fact a strong electrolyte? Well, strong electrolytes include three categories. The first is a soluble salt. That term salt just means an ionic compound. Usually we're talking about, as I mentioned before, a metal and a nonmetal. All of the ionic compounds we're using in today's lab are considered soluble. So you don't have to worry about determining if it is a soluble salt. Second, all 7 of the strong acids are considered strong electrolytes, and I have them listed there. Finally, strong bases are considered strong electrolytes. This includes all of the group 1A elements, as well as calcium, strontium, and barium, which are in the bottom of the group 2A column on the periodic table when they're bound with the hydroxide, or OH, anion. On the previous slide, I brought up the idea of strong acids and strong bases. These are acids and bases that dissociate completely in water, therefore they're strong electrolytes and will conduct electricity well. Given here is a generic equation for what happens when a strong electrolyte is placed into water. Just like a soluble salt, it dissociates completely into its cation and anion. So besides conducting electricity well, something else that happens with a strong acid is that the amount of H+ ion or hydrogen ion is increased when it's put into solution. This can be detected in the laboratory by testing the solution with litmus paper. And so an acid is going to turn blue litmus paper red. Here's another example of a specific strong acid, HI, or hydroiodic acid, dissociating completely into its hydrogen ion and iodide anion. The story for strong bases is very similar to that of strong acids. They dissociate completely, making them strong electrolytes, and therefore they conduct electricity well. Here's an example of what happens when a strong base is placed into water. You can see it dissociates completely, given by a single arrow, into the cation and the hydroxide anion. In fact, it's the presence of this hydroxide anion that defines the presence of a base. This can also be detected using litmus paper, but in the case of a base, we're going to be observing red litmus paper turning blue. Finally, I've given an example of a specific strong base. In this case, it's lithium hydroxide. It completely dissociates when put in water into the lithium cation and hydroxide anion. So there's actually one more category of acids and bases we need to discuss, and those are the weak acids and bases. So we're going to start with weak acids. And this will be the scenario where you might see that in the lab that blue litmus paper turns red, and then when you look at the substance you find that it's not listed as one of the strong acids. So what's happening here? Well, these are acids that partially dissociate into their ions, meaning there's fewer ions in solution, therefore they conduct electricity weakly, and so we call these weak electrolytes. So there's a generic version of a weak acid written here, so HX is partially breaking apart into the H+ cation and the whatever the anion is. And we can symbolically represent this with a double arrow, indicating that not all of the starting material has dissociated into its ions. However, similar to strong acids, they still produce some amount of H+ when put into solution, so that's why we see it turning blue litmus paper red. So let me show you some specific examples. Here's one, it's formic acid. So you see it has this leading hydrogen and then whatever the anion is. In this case, it's a carbon, 2 oxygens, and a hydrogen. So if you were to test this in the laboratory, you would see that it turns blue litmus paper red, but it's certainly not on your list of 7 strong acids. And in this case, the only acidic hydrogen is that leading hydrogen, and that will be the case for all the substances that you test in lab. Now there's one other scenario for weak acids that's a little bit more difficult, and that's the case when the weak acid is hidden inside of a soluble salt. So we're going to look at the case of disodium phosphate. So disodium phosphate, Na2HPO4, is actually a soluble salt. So this is considered a strong electrolyte. However, if you were to test the solution of disodium phosphate with litmus paper, you would find that it still turns blue litmus paper red, and that's because there is an acidic hydrogen in this hydrogen phosphate anion. And so it's this part, this sort of secondary reaction, that's causing the dissociation of the hydrogen from the phosphate. And so it's that secondary reaction that's causing the blue litmus paper to turn red. So just be aware in the laboratory there may be some scenarios where you see the litmus paper change color, but it looks like what you're starting with is a salt. So keep in mind that it's possible that there's sort of a secondary acid-base reaction that might be occurring. As I mentioned, there's another category of bases called weak bases. And like weak acids, these are substances that only cause partial dissociation in water, which means they weakly conduct electricity, and so they fall into the category of weak electrolytes. Now these function a little bit differently than the other substances we've talked about so far because they actually involve water in their reaction. So in this case, B is our weak base, and it's going to accept a proton from water. So you can see in the products it's written as BH+, so the base with an extra hydrogen atom. And then what's left from the water molecule is just the OH-, or the hydroxide anion. Now this process only happens partially, it doesn't happen to completion, and so we represent this with a double arrow. And if you were to test this substance in lab, you would find that it makes red litmus paper turn blue. And that's because ultimately in this reaction, hydroxide anion is a product. And so even though something might not appear to look like a base initially, by testing it with litmus paper in the lab, we can identify it as such and then determine what the reaction that was occurring is, and then you can determine that it's a weak base. So here are some specific examples. As I mentioned, these don't always look like bases, so here's the case of pyridine, C5H5N. This molecule, if tested with litmus paper, will turn red litmus paper blue, and that's because it's accepting a proton from water, which ultimately produces hydroxide anion in solution. The second example is sodium fluoride, and if you look at that, you might think, oh, that's a soluble salt, it's a strong electrolyte. Well, in addition to being a strong electrolyte, it's also a weak base. So yes, that first part of the reaction is a soluble salt and is a strong electrolyte, but there is a secondary reaction that is occurring, just like with the weak bases that we've talked about, where that fluoride anion can accept a proton from water to produce HF and hydroxide anion. So if you were to test sodium fluoride with litmus paper, you would find that it turns red litmus paper blue. So again, just be aware of this possibility in the lab because it's a little bit more difficult to sort of sniff out than some of the other ones. So we've now discussed strong electrolytes, which are those soluble salts, strong acids, and strong bases, and also weak electrolytes, which are our weak acids and weak bases. So let's look at another category of compounds. In this case, let's look at methanol as an example. Does it conduct electricity? Well, if we look at the elements that make up methanol, we see that they're all non-metals. And when this is the case, atoms are generally held together with those covalent bonds, meaning that there isn't charged particles or ions that are part of the structure. So in the case of methanol, the molecules are freely able to move, similar to when we're looking at pure water, but methanol itself is not charged. So methanol, when it's placed in water, does not conduct electricity. This type of compound that does not conduct any electricity is called a non-electrolyte. It produces no ions when it's in solution, therefore it conducts no electricity, and we could certainly put pure water into this category. Other examples of non-electrolytes are caffeine, glucose, and rubbing alcohol. And if you look at their structures, you can see that these are containing a lot of carbon, hydrogen, and oxygen. There's a little bit of nitrogen there in caffeine, but these are all non-metal elements. So if you see a string of elements like this that are representative of non-metals, then you can make some assumption that you're dealing with a non-electrolyte. So let's summarize the information that we've talked about so far today. First, there's a category of electrolytes called strong electrolytes, and these of course conduct electricity strongly. And we're going to do this in the lab by seeing how brightly it lights up a light bulb. So a strong electrolyte is going to cause a light bulb to glow very brightly. These are going to be things like soluble salts, strong acids, and strong bases dissolved in water. If you test the solution and you see that your light bulb is glowing dimly, well then it's likely a weak electrolyte because it's only weakly conducting electricity. This means that that substance is going to fit into the category of a weak acid or a weak base. Finally, if a substance is placed on your electrodes and you don't see your light bulb light up at all, you can call that substance a non-electrolyte, meaning it conducts no electricity. These are going to include things that are molecular compounds, meaning these are going to be all nonmetals that are covalently bound to one another. And remember, they're often going to contain the elements carbon, hydrogen, oxygen, nitrogen, etc. So what are you actually going to do in the lab? For each pair of you, there will be a setup that contains electrodes that are connected to a low voltage power source and a light bulb. And so what you're going to do is test a series of substances and determine based on the light bulb whether it's a strong, weak, or non-electrolyte. So you'll place some of the solution into a little cup, place that cup over the electrode, and then observe what happens to the light bulb. In this case, you can see it's burning rather brightly. So at that point, you're going to record that result, whether it's bright, dim, or off, and then go on and test your next solution. Later in the lab, you'll identify whether it's a strong, weak, or non-electrolyte. If you test a solution and the light bulb does not turn on at all, you can determine that it's a non-electrolyte and you're done testing that substance. Now, if it's dim or bright on the light bulb, you're going to want to do an additional test to see if it's acidic, basic, or neither. And you're going to do this by taking your glass stirring rod and dipping it into the solution and touching it once on blue litmus paper and once on red litmus paper. You do not want to take the litmus paper and dip it into the beaker. This is wasteful of litmus paper. If you use the glass stirring rod in the way that's directed, you should be able to test 3 or 4 different solutions all on a single piece of litmus paper, reducing the waste in the lab. For this particular case, you can see that neither the blue or the red litmus paper changed color much at all. So what conclusion can you draw about this particular substance? Is it an acid, a base, or neither? So now that you have some general sense of what the laboratory procedure will look like, you want to reflect that in your laboratory notebook before you come to lab so that you're ready to get started when you arrive. So I'm going to check everybody's notebook to make sure you've both written in pen and that you've completed this short assignment before you get started so that I'm sure that you're prepared to begin. So you need to put your name on the top of the page, and that's true for every time we do a lab. Actually, every page of the lab notebook needs to have your name on it. Next, you're going to write the heading Purpose, and you're going to then write the purpose of this lab. So you can look back through this lecture and use my wording for what the purpose is, or based on what you've heard, you can come up with your own verbiage for the purpose of this lab. But it should be 1 or 2 sentences describing the reason that we are performing the lab. The next section in your notebook, you're going to put the heading Data, and you're going to prepare a data table, and it's going to need 3 columns labeled Substance, then Light, then Litmus Test. And I think we're testing about 21 substances, so you're going to need 20 about 21 horizontal lines to be recording your data in the lab. So just make a note to yourself too, as you're testing these substances, what you're going to be recording is, of course, you're going to write down what the substance is in the substance column. In the light column, depending on your result in the lab, you're going to write either bright, dim, or none, or off, or whatever represents a non-electrolyte. And then in the litmus test column, again, this is only if your light turns bright or dim will you do the litmus test, and you'll write either red to blue, blue to red, or none. And you're ultimately going to use these results to fill in a report sheet that you'll turn in. So just keep in mind the type of data that you'll be recording in this table. So again, just to reiterate, what you need to have done before you come to lab is just your name, a purpose, and then the blank table. And then you're going to need to take the check for understanding that is in the same folder on Angel. And then when you arrive to lab, you're going to work with a couple other students, including your lab partner, to answer a few questions just to make 100% sure you're ready to perform the experiment. If you have any questions, please let me know before lab begins.